All right, well, now we don't have to worry about detasseling now that we're doing trees, right? Whatever arborist does with trees instead. But today what we're going to do is we're going to continue on trees and tree-based data structures. Last time I took you through implementations of the pre-order traversal. And what I want to do now is I want to show you, basically, we're going to walk through the other two traversal strategies, in-order traversal and post-order traversal. And then I will briefly show you how to implement those as well. So what I've got over here is, well, once I open it back up, the same tree that we were working on before. But now let's go through an in-order traversal and a post-order traversal. We'll start with an in-order traversal. And we did pre-order traversal last time, right? Yeah, okay, good. Remember that an in-order traversal goes with a left, then root, then right. Right? When we start at the root here, we don't immediately process it. Instead, we go down to the left subtree, and only once we're done with this entire left subtree do we process the root, and then we go down and do the right subtree. Well, you do this recursively, basically, or inductively. That when you go down to the left subtree here, you don't immediately do the root of that subtree. You go to the left. Right? You do everything down here, then the root, and then everything over here. So what is the, I'll start at the root, but then I'll go left, 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 left. So where do I actually start? At L here. L is the first thing to get processed. Now, technically, L's left child would get processed first, but it doesn't exist. Then L would get processed, and then L's right child, but again, that doesn't exist. Okay? So after we're done with L here, what's the next thing that gets processed? G, right? Because, again, basically we're right here. We process the left subtree, which was just L. Then we process G, and then we process its right subtree. Okay? So after that's been done, then what's the next thing that we do? We go down to M, but we don't immediately process it. Instead, we process its left subtree, then we process M, then we process its right subtree, but there's nothing to process there. So we have R, M, and then nothing. Right? And that takes care of this entire first subtree over here. Okay? Fast forward a little bit more, it's going to be D, because we've done its left subtree, then we do the root, then we do the right. Right? Fast forward a little bit, H, but we do its left subtree, which is empty, so then H, then N. Right? And at that point, we're done with this entire subtree. So B, then what? We go down to E, process E's left subtree, which is empty, so we end up processing E, then IO or OI? OI. And at that point, that takes care of the entire left subtree hanging off of A. Then we process A, and we move on to its right subtree. So very quickly here, what about that last subtree? What's the order there? All right, C, P, then J, Q, right? This subtree right here, right? That's what I just processed. After I'm done with that, F, and then K. Right? Any questions on the order that I went in there? No? Okay. Oh yeah, go ahead.
How do you keep track of the ones you processed already?
That's a good question. How did we do it with pre-order traversal? A stack. Or what's the alternative? Recursion. So let's discuss that solution first. So here's my in-order traversal. I'll go ahead and get rid of this so it actually compiles here. So remember, so you can do it either way. I'm going to show you the recursive way, okay? Here we've got our recursive preorder traversal that creates a list. That's the result that we're going to put things into the list and then print it out. And then it kicks it off by calling the recursive preorder traversal on starting at this root, okay? What we're going to do is we're going to call a recursive in-order traversal. Now to do that, I'm going to go ahead and cut and paste the recursive preorder traversal and rename it to in-order traversal. Obviously, I'm probably going to want to call it recursively if there is a left child, if there is a right child. But what is the difference? With a preorder traversal, I processed the node, then I went left, then I went right. With an in-order traversal, I want to go right before I process the node, and then I go left. The only thing I need to do is what? Move that first step to the second step. Right? Now, let's go ahead and recursive in-order traversal. Where's my toString method? Oh, did I get rid of it? Oh, darn it. Okay. So then toString. Public string toString. Return this recursive in-order traversal, and then call toString. Right? And let's see if we get the same order as we got over here. LGR MDH, LGR MDH, PJ Q FK. Looks like it's correct to me. All I had to do was, there were 3 steps, right? Go process it, go left, go right. All I had to do is take one of those steps and move it in the recursive solution and get a completely different ordering with an in-order traversal. All right? Let's go with a post-order traversal now. Same exact tree here of a binary tree. There we go. Same exact tree, but now let's do a post-order traversal. Now remember, with the post-order traversal, you're going to go left, then right, then root. Right? So if I were just looking at this subtree right here, the order that I would go in is I would take care of the left, then the right, and then the root. So it would end up being P, Q, J. Okay? Let's do that for the entire tree, though. Immediately, what can you tell me about where A is going to be, where the root is going to be? At the very end. I do left, then I do right, and then I do this node. What can you tell me about where A is on an in-order traversal? In the middle, whatever that means. Middle here means all of these elements to the left were in the left subtree. All of these elements to the right were in the right subtree. And A stood right in the middle there. Right? With this one, A is going to be the last. But we have to get there first, right? So I'm going to start at A, and I go left, 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 and I'm left with one single node here. Normally, I would go to the left subtree, but it doesn't exist. Then I would go to the right subtree, but it doesn't exist. And so I end up processing L first. Okay? And I'm done with L. Now, I come back up to G, but I don't process G. I take care of the right subtree first. So now I'm down here at M. I don't process M. I take care of the left subtree, then the right subtree, then M. So that's going to be R, and there is no right subtree, and so I end up with M. Now, the L and the left subtree and the right subtree have been processed for G. Now I take care of G. And that left subtree hanging off of D is done. So I go to the right, but I don't process D. Instead, I go to the right subtree. I'm at H now. I take care of the left subtree, which does not exist, then the right subtree, which is just N, then H. So N, H. At that point, I am done with the left subtree and the right subtree of D, and so I can free to process D. Fast forward a little bit. What's next? O. Then I's right subtree, which is empty. Then we can take care of I. E's left subtree is non-existent. We just took care of E's right subtree. So now we do E. And finally B. All right? We don't process A. We take care of its right subtree first. Fast forward through all of that. We take care of P, Q, J, just as I said before. Then we take care of K. Then F, because it's we took care of K, then F. Then we're free to take care of C and then A. Okay? Now how do we do this one recursively? So I will restore this now. Recursive postorder traversal. What would that look like? It would look like the recursive inorder or preorder traversal, but where do I process the node? At the very end. And let's change the toString method here to use a postorder traversal instead of an inorder traversal. Why are you complaining? Oh, I never changed the name, sorry. There we go. Now you should be happy. It should be okay, right? Nope. What did I do? Postorder traversal, recursive postorder traversal, recursive postorder traversal, recursive postorder traversal. And that should be it, right? And then postorder traversal.
We need to somehow keep track of,
Oops, there's something wrong here.
do we somehow need to keep track of, like, what the root node was?
Well, that's being kept track of by the recursion, right? I'm at the current node here, and I'm in a stack frame. All right, and that current node is a local, or it's a parameter variable that's being stored in your stack frame. You make another function call, function call, function call. When you eventually return, it's being kept track of on the stack, the call stack itself for you. Right? All right, so recursive postorder traversal, recursive postorder traversal. Uh-oh, 2, 3, 1. Oh, there we go. That's why. Of course, I need to call. Otherwise, it wasn't recursive. It was just calling the inorder traversal. There we go. Now we get L, R, M, G, N, blah, 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 blah. P, Q, J, K, F, C, A. I am convinced. P, Q, J, P, Q, J, K, F, C, A. Right. Good question here would be, remember that these are the recursive versions. Down here with the preorder traversal non-recursive version, right? We just used a stack. So what might that look like for a postorder traversal and an inorder traversal using a stack? Well, if you're really interested, go ahead and take a look at the book because I have full pseudocode in there. But what I want to do is I want to just give you the idea. We're not going to go through the details of actually programming it. Instead, I just want to give you the idea of why it is easy to do. All you need to keep track of is where you are, the current node, and where you've been so that you know where you're going, right? Makes sense because you are traversing through this graph. If you're searching through a city, right, or searching through a maze, you simply need to know where you are, where you've been, and where you're going. And you can go anywhere. Right? So here's the idea. Say that you're at a current node U. You could have gotten here any number of ways. You could have gotten here by coming from the parent. You could have gotten here by returning from the left child. Or you could have gotten here by returning from the right child. So I'm at U right now. If you came from the parent, ... or the left, or the right. Right? So let's take the first case here, that I came from the parent. Where should I be going next? Go to ... Right? regardless of whether it's preorder, inorder, or postorder traversal. If I come from the parent, where am I going to go next? To the left. Go left. If I came from, I'm returning from the recursion basically, from the left child, where do I go next? I go right. So if I come from the left, I go right. And finally, if I'm returning after having processed the right subtree, where do I go now? Back to the parent. Right? If you're coming from here, then you go here. If you're coming back from the left, then you go to the right. If you're coming back from the right, then you go to the parent. Now, in each one of these three cases, it tells you when to process the node. Process you if. Now, in the first case, I've come from the parent and I'm going to go to the left. If I want to process it right now, then what kind of traversal is that? I come from the parent, I process it immediately, then I go left. That's a preorder traversal. If I'm coming from the left, and now I need to process it before I go right, then what kind of traversal is that? Inorder. Right? And if I'm coming from the right, and I'm about to go back to the parent, but before I do, I process it, then it's a postorder traversal. Yeah?
Why is that significant if we're like doing like a post-order thing?
Well, I mean, it's not, but this is the basic idea. Use a stack, use these rules. If you just wanted a post-order traversal, you use the third rule, and that's it, right? If you wanted the pre-order traversal, you would use the first rule, and that's it, and a stack. In fact, you don't even need to use a stack, as long as you have these three simple rules. Let me go ahead and restore the original binary tree here. Come on. There we go. All right. Now, think about what we were doing in all three cases. We started at the root and then went left. We went left, we went left, we went left. We would have gone left, but there is no left subtree. Then we would have returned and gone to the right subtree, but there was no right subtree. So in other words, we're just coming back up. Then we go down to the right subtree and continue. And now I'm not going to draw arrows anymore. What am I doing? I'm treating this like a perimeter, right? And I'm walking around I'm treating it like this series of walls, right? This building, and I'm just going around the outside of the building, traversing all the walls. And depending on those local rules, right? All you need to do is keep track of where you've been, the previous node, and then if you're going up, that's the current node. Right? I came from that node, therefore I'm coming from my right child, or I came from that node, I'm coming from my parent, or I came from that node, I'm coming from my left child. And all I have to do is apply these three rules. In other words, I can do this with no data structures whatsoever. And it's a tree walk, right? That's called a tree walk. Why is it called a tree walk? Well, I'm walking around the tree. I'm just walking around the perimeter of the tree, okay? There's one more that I want to show you. There we go. So, if we read this like I wrote it, A, B, C, D, E, F, G, right? We start at the top and go top to bottom, left to right. So here's another traversal strategy. I visit A first, and then I go down to the next line, and I visit those in the second level next. Then I go back all the way to the beginning and do this and continue. Top to bottom, left to right, okay? That's called a breadth first search. Breadth first search. Now, why is it called a breadth first search? Let me go ahead and get rid of all these scratchings. Right? And look at it with respect to the distance from the root. That one is a distance 0 from the root. These two are a distance 1 from the root. Distance 2, distance 3, distance 4, distance 5. And you'll note here that I drew them as curves. Because what we were doing before is what's called a depth first search. If you want to think of it like a maze, right? You're looking for the way out. You're looking for a particular spot in the maze. You can go as deep as you want into the maze. When you hit a dead end, you backtrack and try deeper, some other way of going through the maze, but as deep as you can. You go as deep as you can until you hit a dead end. And then and only then do you start backtracking. But there are other ways of searching an area. If you were actually searching for, say, a missing person, you would go to the place that you last saw them. And would you immediately go off 10 miles in one direction, looking for them that way? And then, oh, I didn't find them that way. Go all the way back to the beginning. Go out 10 miles that way, right? No. Logically, if they were missing, then they would be close by, right? They wouldn't have gone 10 miles in, say, like the last half hour or something like that, right? If they were on foot. So what do? You search in a perimeter. You search in a perimeter, say, a radius of 50 feet, then 100 feet, and then 150 feet, right? You keep expanding your search radius until you find the person or you've exhausted all the possibilities. So that's what a breadth first search does. It searches things that are close to the root first before expanding its search out to things that are further away from the root. How might we do this? So let me decrease the size there. I'm going to set up another data structure here. Remember, I'm reading it top to bottom, left to right. So what I'll do is I'll put in A at first. And then I will bring it out and process X. Right? I'm going to just call it X. And initially, because I start at the root, that was A. And so here's my order, BFS order down here, A. It's not going to be all that interesting because if you read it top to bottom, left to right, what do you get? A, B, C, D, E, F, G, right? So C, D, E, F, G, dot, dot, dot. That's just because that's the way I wrote it, and that's natural, right? Okay. But once I process X, what I'm going to do is I'm going to do something to X's left child and X's right child. Right? I'm going to set myself up for the next iteration. I'm going to put B in and then C. And so that the next iteration in this loop here, I'm going to pull out the next one, which is B, and I'm going to do the same thing. I'm going to process B, and then I'm going to insert B's left child and B's right child, which happen to be D and E. C is still in this data structure up here, available for me because I still need to visit it and process it. What is this data structure right here? Things go in one end and they come out the other. That's a queue. Right? So a queue-based data structure gives us a breadth first search. Let's implement it. In fact, I'm going to implement it right here. I'm going to borrow a whole bunch of stuff. And I'm going to call this a breadth first search, breadth first search traversal. All right. Instead of a stack, I've got a queue. And now it's still a deck, right? Because a deck is a double-ended queue. You can put stuff in and take stuff out from both ends. Okay? And the linked list implementation is the one that I'm going to be using. Okay. If the root is null, I'll just immediately return an empty list. We're good on that. Right. Return result down here. So what should it look like? How do I initialize this? I need to put in the root, right? I've already created my queue, and that I'm calling it queue right there. So queue dot add last, right? This dot root. Right? So if I'm adding last, then I'll remove first. Right? You could go ahead and add first, remove last if you wanted to, or you can turn your queue around and it doesn't matter, right? You're working from one end is insertion, the other end is removal, okay? Now I'm going to go into a loop. While the queue is not empty, while it's not empty, oops, can't type today. Then what am I going to do? I'm going to do this process. I'm going to pull it out and process it. Then I'm going to, in NQ it's left child, NQ it's right child. So, what? Tree node T, I'll even call it X, the same thing here. Q dot, if I add last, then I should remove first. There we go. Process it. So by processing, we mean result.add x's value. And then finally, I take care of its left child and right child. Sounds very familiar. I'm going to steal the code from the preorder traversal down here. Except for in the preorder traversal, I went right and left. Why? Because it was last in, first out. So in this case, I'm going to go left, then right, because it's first in, first out. And that'll be X and X. And instead of a stack, I'm using a queue. I stole most of this code from a preorder traversal, didn't I? Right? So this is exactly the same code, except that instead of using a stack, I'm using a queue. This is all essentially the same code. Instead of pushing and pulling, I am in-queuing and de-queuing. Right? It's the same basic idea, though. I put stuff in, I take stuff out. I put stuff in, I take stuff out. The only difference is one of them is a queue and one of them is a stack. That goes back to one of the central themes of this course. Smart data structures and dumb code are a lot better than the other way around. Both of these are dumb code. Put stuff in, take stuff out, put stuff in, take stuff out. If I swap my choice of data structure, I get a completely different ordering with completely different applications, right? And all the work, all the heavy lifting is done by the data structures themselves instead of my code. Right? Yeah?
Should we be using push with the queue?
No, because push and pull. Oh, sorry, this one?
Yeah.
You're right. So I add, what do? I add last. Thank you. That would have come through if we tested it, and let's test it now. What should I get if I do a breadth first search traversal here? I should get A, B, C, D, E, alphabet up to R, yes. And I do. Smart data structures and dumb code are a lot better than the other way around. Right? Cool. Okay. So that's a preorder traversal, inorder traversal, postorder traversal of trees. We've looked at stack-based solutions. We've looked at breadth first search, which is a queue-based solution. Okay. All right. I want to add even more structure. All right. Remember, the whole purpose of using trees is because we started out with these general graphs, right? General graphs can have any structure that you want. Then we said, all right, well, throw out cycles. That gives us trees. Now orient those trees, right? That gives us direction, top to bottom, left to right. Restrict those so that they only have at most 2 children. Now we've got binary trees. Let's add even more structure onto that. The structure that I want to add are called binary search trees, right? So here's the definition. A binary search tree is a binary tree, so it's still a binary tree. It still has at most 2 children for every node, except now that we've associated keys with them. With every node, there's a key. Instead of A, B, C, D, E, F, G, we're going to use integers because integers are orderable. 10 comes before 20. It'll be easy, right? The binary search tree property is such that every node has a key k, right? Such that every node in a left subtree is less than k. Every node in the right subtree is greater than k. Okay? And once again, let's go back to an example here. Come on. search tree. There we go. That's almost the same structure. Is it the same structure? Yes. It's the same structure. I've just given them key values. Okay. Now let's make some observations here. At the very root here is 50. Look at all the nodes over here in the left subtree. They're all less than 50. All the nodes over here in the right subtree are all greater than 50. What if I allowed duplicates? What if I had two 50s? The middle child. No longer a binary tree though, right? You can't have ternary trees, quaternary trees, or in general B trees, where B is some range. It can have between 25 and 50 children or something like that, right? We're not going to do that though. If you allow duplicates, first of all, you can design your data structure so that it doesn't allow duplicates. That if you have two things that are truly, truly equal, well, you only have one copy, in which case you have a set, or you need to break those ties some way, right? And that's usually done by taking the Java virtual machine memory address, because everything, if they're different, they will have a different memory address in memory, so you can use that as a tiebreaker at the end of the day. Or if you really wanted to support duplicates, you have to choose a side. You have to choose a lane. Everything over here is less than or equal to, and everything over here is greater than. Or you could go the other way. Everything over here is strictly less than, and everything over here is strictly greater than or equal to. But you can't have the case where this is greater than or equal to, and it's either one. Because now 50, where's that second 50? Is it in the left tree or the right tree? Could be, either one, right? And we don't want that. Because we're going to exploit the structure now. Hopefully you can see how we can exploit it. What if I wanted to search for something? Search for 10. No, let's go with 24. That's interesting. All right. What do? You start at the root. And because of the binary search tree property, you know, well, 50 is not the thing that we're looking for, right? If we were searching for 50, guess what? We got lucky. We found it at the root. We're done. How many comparisons did I need to make to find that? Just one. Can't always assume you're lucky, just like linear search, though, or binary search. If you got lucky, you found it right in the middle, right? So let's search for 24. Because of the binary search tree property, we know that if 24 exists, it must be in the left subtree. It can't be in the right subtree because it's everything in that right subtree is greater than 50. So now I'm over here at 40. If 24 exists, I know that it must be in the left subtree. 20. Now I know that it should be in the right subtree because 24 is greater. And at that point, I'm done. I found what I'm looking for. How many comparisons? 1, 2, 3, 4. So comps, 4. Let's search for 12. Right? So again, less, greater, less. I found it. How many comparisons to do that? 6. All right, let's search for something that doesn't exist. Let's search for 42. How's that going to go? 50, less, greater, less. Uh-oh. If 42 had existed, it would be right here. How do I know that I should stop? Because there's no child there, right? I've fallen off the edge of the tree. How many comparisons did it take to get there? 1, 2, 3, right? At most, how many comparisons do you need to make for any tree? This was the worst case scenario right here when we searched for 12. How many did we have to make? 6. How does that relate to the topology or the shape of this tree? It's the maximum, we call that depth, right? What's the depth of this tree? The depth of any one node is the length of the path from the root to that node. The depth of 45 is 2. The depth of 2 is 1, 2, 3, 4. The depth of a tree is the maximum depth of any node, or maximal depth of any node. And this is the deepest node, so 1, 2, 3, 4, 5. How does that relate to the maximum number of comparisons? Depth plus 1. So, observation, or observations, right? To search only requires a number of comparisons proportional to the key's depth, right? Thus, the maximum number of comparisons is D plus 1, which is order D. Now, is there a guarantee on the depth? If you can ensure a balanced or full tree. Remember, we did this analysis that if we had a full binary search tree with n elements, what's its depth? Well, it would end up being 2 to the d, then we solve for d. So the opposite of that is going to be log of n, right? i.e. search will be order log n. And we've done what we hope to do, right? Why are you not? There we go. There, order log n, right? In other words, we're matching the best case scenario with binary search, but we don't have to have a contiguous array. Not only that, but all the other operations are also going to be proportional to the depth, as we'll see here very shortly. All right. That's insertion, or that's searching. Okay. Before we go on to the other operations, let's create a binary search tree. Right? So I've got this nice binary tree already, right? It'd be a shame to lose all of that functionality, because you might want to do a preorder traversal on a binary search tree. You might want to do a postorder traversal on a binary search tree. You might want to do an in-order traversal on a binary search tree. Why? Do an in-order traversal on this. In other words, do the entire left subtree, then the right then the root, then the right subtree. What's the first thing that's going to get enumerated in an in-order traversal on this tree? 2. Then what? 10. Remember, 2, then 10, then the right subtree. Now we're in the right subtree, so I do 12, then 15, then nothing. Gee, I wonder why we call it in-order traversal. Right? Because it's in order when you've got a binary search tree. Right? Okay. So I don't want to lose that functionality. Should I go ahead and copy pasta binary tree? Or you know what, maybe just binary search tree, rename it. Are all binary trees binary search trees? Nope. Are all binary search trees binary trees? That's how I defined it. A binary search tree is a binary tree. Now put on your object-oriented programming thinking cap, right? Is a. That tells me inheritance, right? What if I created a binary search tree, parameterized on T, and I extended binary tree, also parameterized? Now I get all that lovely functionality that I've already done up there, right? In order traversal, all that stuff. But a binary search tree is not just a binary tree. What else is it? It's order, right? How do we order things? How do we order integers? Well, I'm looking at the integers. I know how to order those. Do I have integers over here, though? Nope, this is not a binary search tree for integers. It's not a binary search tree for strings. It is a binary search tree for blah, t's. So how do I order things that I have no idea what they are? I have to make it comparable, or more generally, a comparator, right? If I make that part of the state, private, final, comparator, I'll just call it CMP. Right? I have to bring that in, of course. There. And I will want a public binary search tree comparator for t's. This.cmp equals cmp. Right? Now I've got a root. The root, by the way, is being inherited. That's why I made it protected, because I knew I was going to want to subclass this. So I made it protected so that I can see it in the subclass. But I've also got a comparator. So I can do this kind of algorithm over here. Start at the root and search for something. Let's implement that. Public, Boolean, contains. Right? Could I do index of? Does that make any sense? Does it make sense to index something on a tree? Huh? Right? I guess you could dump it to a list by using an Inorder traversal and then look up the index, but that doesn't make much sense. Right? So I will have contains. This will return true if it contains the key that you provided here, an element of type T, and I'll call it a needle, right? Because you are searching the haystack, and it's looking more and more like a haystack, right? Now that it's got this structure, you're searching for a needle in this haystack, okay? And that's why I'm going to call it needle. Right? I'm going to return true if it's in there, false if it's not. All right, help me out. How do I go about codifying that algorithm here? Well, how did I start out? Where do you start? At the root. And then make a comparison. Is the root what I'm looking for? Let's just do at least that part. Right? So tree node, T. I'm not going to call it root. I'm going to call it the current tree node that I'm standing on right now. And so I'm going to step on this tree's root. Now I'm standing on the root of the tree. And I want to know, is this the thing that I'm looking for? Is the current node, is the value stored in that equal to the needle that I'm searching for? I can't do something like this. If the needle is equal to the current, then return true. Can I do that? First of all, needle is what type? T. But the current is what type? Tree node. Right? So the integer is not the same thing as a tree node. It's perfectly happy compiling, by the way. I mean, it's not compiling because of other reasons, but this line right here, this comparison, it's perfectly happy with that. Why? For the same reason that it's happy if you perfectly happy if you say this string is it equals that string is hello equal hello. That's never going to be true. That's hardly ever going to be true. Why? Because equals is a reference operator. Right? Is that thing stored in memory the same thing as that thing stored in memory? For a string, you have to go dot equals or compare to if it's comparable. Here, I'm going to use the comparator. Compare the needle and the current equals 0. Right? And here it's not going to let me compile because now it can see that the needle is of type T and the current is of type tree node. So what I need to do is get the value stored at that tree node. Now the comparator should be happy. Why are you? Oh, dot compare. There we go. Right. Now, if it's 0, then that means that the needle matches the value. The needle 50 matches this value right here. Right? But that's not all I want, right? What if I'm searching for something else? What if I'm searching for 12 Should I stop at the root? Nope. I need to make another decision. What do I do? If it's not the thing that I'm searching for, then I need to know, do I go left or do I go right? Right? So else if, this comparator is less than 0, that means that the needle would come before the current value. So where should I go? The needle is strictly less than the value. So where should I go? Go left. Right? By updating the current node to be current left child. Right? Else if, and this else if is not strictly speaking necessary, but I'm going to do it just for demonstration purposes because it's either one, the other, or the third. Right? If it's greater, then where do I go? Right.
You check if the left and the right exist.
Good question. We don't even have a loop yet, do we?
No.
So I'm just getting the basic get right child. There we go. I've only got one iteration here. You're standing on a node, current, and that's what you're looking for, or you need to go left, or you need to go right. How and when do I stop? On a successful search, if I search for 12, of course I'm stopping on that 12. But what if I end up searching for 42 here? I end up falling off the edge of the the tree, right? At which point the current node that I'm standing on is what? Null. So while the current is not null, continue this process. Go left, go right, whatever. Once you've fallen off the tree, though, what can you say? Was there a 42? Nope. So what do you return? False. There. Okay. Now I've got a binary search tree demo over here. Pay no attention until I get back over. There we go. All right, now let me expand this out and show you what it's doing. I'm just going to call this T. Right? I create a new binary search tree. I create a comparator that simply compares integers, and it'll compare them in ascending order, 10, 20, 30, 40, whatever. Then I went through and arduously reproduced this entire graph by manually creating all of these nodes, setting all their parents, all their children, et cetera, et cetera, et cetera. So now let's test it. All right. System.out.println actually I never said it right. So there are a bunch of nodes here, and t.root is going to end up being n50. So I didn't lose for the forest for the trees. I used kind of bad naming conventions. N for node, and then the number that it contained, so that I could easily reproduce this graph right here. Right? So does t dot contain, does it contain 50? What would you expect this to output?
Yes.
True. Excellent, it does. Search for something else. What else did we search for? 24? That should be true. True. It's up here, right? What else should we search for? 42. This should be false. Hey, looks like it works. Right? Not only that, but it's going to be proportional to the depth of the tree. So super, super efficient. It's basically binary search efficient. But we have the best of both worlds. We have efficient search by this divide and conquer approach, but we're not tied to a sorted array of elements that forces us to use random access. Yeah? Say again? 45?
Yeah.
It's a root of a subtree, if that's what you mean.
Well, if we're like
Oh, then it wouldn't necessarily, we'll talk about other operations here shortly, but we're just talking about searching right now, right? Another question?
No, I was gonna add how like adding or subtracting like nodes works here.
Okay, yeah, let's do that then, all right? That's just searching, binary search trees, right? How did we build this tree to begin with? Right? How do we add elements? And so I'm not going to start with an empty tree. Instead, I'm going to go ahead and start with the same tree as before. But now how do we say insert elements? Insert elements. Well, let's insert that one that we didn't see, 42. Where would it go? Right here, right? Well, how do we know that it goes right there? We start at 50, go down to 40, 45. Oh, okay, there's room for it right here. Or we find what we're looking at. If I tried to insert, say, instead of 42, what if I tried to insert 40? Are we going to allow duplicates or not? 40, it's already there. Let's not allow duplicates. We can throw an exception. We can do no operation. We can return false. It had no effect, right? We could do a bunch of other things depending on what we want to design. But for now, let's just go ahead and not allow duplicates and go ahead and insert this. So how do we do this? Search for where it would be. Right? And if it's not there, insert it as a new. If I end up inserting 42 here, what is it? It has no children, of course, because I've just inserted it. It's called a leaf, right? So that's insertion. Let's go ahead and implement it before we do deletion. And this might be the only other thing that we're able to do today. All right, so public void insert, and it'll be what, element. So T, new element. I'll just call it element. Right. I need to search for where it would be. Right. In other words, I need to search for. It would be here, right? If it existed. But what I need is I need its parent, because when I insert it, I'm going to want to make that relationship. Right? So what I need to do is I need to stop short. I need to basically repeat this search algorithm right here. Right? And I'm going to put that into another method. I'm going to say get parent of. And this will still be my needle. It'll be a tree node. Right? What I'm going to do is, I want to know who, here's this node 42. I want to know what their parent is because I'm going to end up inserting it right there, right? As the parent. Should I make this public? Probably not. Why? Leaky abstraction. This is a binary search tree node. What the hell is that, right? It's a stuff that I put in. Should I be able to get out that node right in the center of the tree and then like start slashing at it and pruning it? Probably not. I want to leave that to the class itself. I don't want to expose those details to the outside world because I don't want you screwing up my tree. Right? I'm the tree now. Right? I don't want you, the outside world, screwing it up. Right? Okay. I start at the root. If that's the thing I'm searching for, then well, actually I need to stop short, right? So instead, I'll probably want a current and a what? Previous. I'll go ahead and shorten it up to current and prev. Right? And I'll go ahead and make the previous null because if I start at the root, where did I come from? Nowhere. I just started there. Okay. Now, while the current is not null, I will continue searching for it. Okay. If this is the thing that I'm searching for, then, oh, guess what? you're trying to insert this needle, it already exists. So return what? Null, maybe? No operation. We could throw an exception, something like that, whatever. So what I'm going to do here is if the needle exists, return null as a flag value, indicating that you shouldn't be inserting this because it's already in the tree.
But you're just asking for the parent of the needle.
Right. So let's go ahead and complete this. Right. So I'm going to move the current to the previous, and then update the current to its left child, right child. Right. Current. Current. Right. When I break out of this loop, well, first of all, if I don't break out of this loop, if I ever return, then I know that I found my needle. I shouldn't put two needles of the same type in. Right? That'll return null. Otherwise, what I'll do is I've broken out of this loop. Now that I've broken out of this loop, what does the picture look like? This is my previous, and this is my current, which is null. Right? So which one do I need to return? Previous. That gives me the parent. Right? All I'm doing is keeping track of the last step. The current step and my previous last step. Move forward, move forward, move forward. And I'm always keeping track of my previous. Okay? Now, insert. Except before we start using that, let's think of an edge case here. What's one edge case that we need to take care of? The root. If this root is null, then that means that you're inserting into an empty tree. How do you insert into an empty tree? There you go. Right. Else, and I'm not going to put the else here because I'm just going to go ahead and get the parent of the needle. Once I've got the parent of that, what do I need to do? I've got the parent. I need to create the current node. I guess I should have done that up here. Tree node t new node is equal to this thing. And then what I can do is I could just make this new node. There you go. And then, but now I've got the new node as well, right? And then I need to get the parent. There. New node dot set parent to the parent. What that does is it makes this current node refer back to its parent. And now I need to make the parent refer to this current node. So parent dot set left child or set right child to the new node. Which one is it? Left or right? I need to compare, right? Do I should I be the left child or should I be the right child? So if this.cmp.compare my parent dot get value and the new node dot get value, right? So if the parent is less than the new node, where should it go? To the right. Else it should go to the left. So if you want to make it left, right, I like this. I like this better. I don't know. There we go. If, why are you complaining? If, blah, 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 blah. Do I not have enough parentheses? I do. What are you griping about? Oh, not enough closing brackets. There, now. Now it's happy. Right? Now that I've successfully done this, we haven't tested it yet, right? Let's go ahead and use that return value now. Void. If we ended up, in fact, we didn't take care of that, that situation. What happens if the parent of is null? The needle exists. What should we have done? Would this have worked if the parent were null? Nope. So if the parent is null, that means that the key already exists. And so we'll just return. Don't do anything, right? 42 is already in the tree. But now let's go ahead and use this return value, Boolean. I'm going to change it to a Boolean. If you had no effect on the tree, I'll go ahead and return false. You didn't do anything, right? Here, if you're creating a new root, you would return true. Yes, you're putting in a brand new root here. And likewise, either one of these is going to return true. You had an effect on the tree. Okay? Let's try it out. So it's not in there, so it should be false. Let's go ahead and put it in there, or insert 42. There we go. And so the second call should be true. So it should be, print out false, then true, right? Ooh, darn it. Oh, compilation problems. What? What are you complaining about? Come on. Oh, nobody called me on that? Current, there we go. All right, now I'm crossing my fingers here. Again, what should it be? False, then true. Awesome. 42 is now in there. Now, how do I know that I put it in the right spot? Well, I have some evidence here because if I didn't put it in the right spot, contains might not work anymore. I could have two bugs, right? One bug makes the second bug correct, right? And so I would have other bugs that would also manifest. Is this a proper way of testing? Probably not. What would you want to do? Okay, you could print it out somehow. I have written code. In fact, do you know how I didn't draw this? Guess how I created this graph or this tree here. Oh, I used LaTeX and Tixie, yes, but I didn't write. I didn't go put the first node here, put the second node here, like I did with this stuff. What did I do? I wrote code to do it for me. Right? It prints out Tixie code that then compiles into this thing. Right? So I would do it. You could do it that way visually, but what's an even better way of doing it? Well, you'll find out in Lab 15. Right? Lab 15, binary search tree tests. What does it look like? Well, here, that's what I should have done with that integer comparator. It adds all those elements, makes sure that they exist, and then it also does it? No, unfortunately, no, it doesn't. But it's much more rigorous, right? It puts things in, and is there even like there should be like a, nope, I just hard-coded a bunch of these tests. In fact, I think somebody else, Hunter might have done this or helped me do it. But there's the expected order if I do a post-order traversal. So the likelihood that you had multiple bugs, all that canceled each other out with all of these tests is very, very unlikely. And this is one thing that we mean when we talk code coverage with tests, right? Don't just have one test to test one line. Have multiple tests to cover as many lines as you can, right? And if they all pass, then with very high probability, you don't have any bugs, right? If one passes and one fails, then, well, you know that there's a bug in there already, right? But by having the larger and larger amount of tests that you have, the higher and higher assurance you have that you have no bugs as long as they're all passing. Okay. All right. Any questions on this? No? So then how do we delete things?
Yeah, that would have been my question.
We'll do the details next time, but how do I delete 50? Delete it? Okay. Then what does that look like? Now you've got a forest.
That's it?
No, no, you can't do that.
Okay, I was gonna say that I.
Oh, okay, you could do something like this. Like now 60 is the new root.
Well, if
Right.
60 has a child, then use the child.
Yeah, what if it had a child? What if it had a, I don't know, what could it be?
Use,
55?
use the child. So find the first right.
Oh, don't jump to the solution. Come on, give me the stock bad answers first, so that we can. No, I call those Gomer answers, right? If you check out the last homework, I love these kinds of homework questions because, over the years, you get bad answers, and every time I get a bad answer, wow, that's great because it shows a fundamental misunderstanding of what happened. You take that and you turn it into a Gomer question. Gomer thinks he can do this, and so why can't he do it? And there's your question that you give to the future students, right? And the Gomer questions turn out to be great because one, they don't end up getting automatically the same misconception, right? They don't give that bad answer because they see the bad answer. I tell them that it's a bad answer. Then they have to think through why it's a bad answer. And I use Gomer because of Gomer Pyle. We know him. No, Gomer, he was the idiot private in the army. It was an old TV show before my time even, right?
Is it black or white? Yeah.
Yeah, he was. Oh, no, sorry, I'm so stupid. Always it was a comedy, right? So Gomer Pyle, and nobody's really named Gomer, so that's why. I mean, if I went and said, Joe, and then I would offend all the Joes. But nobody's named Gomer, or at least I've never seen an actual Gomer. So those are great Gomer questions. Why does this idea not work? Right? But we'll go ahead and come up with the correct solution next week.
I just call them the meta answers.